Dear students, welcome to all of you. Now we discuss multiple choice question paper CC-6 semester 3 CBCS mathematics honors ring theory and linear algebra 1. paper CC-6 question number 1a. The integral domain of matrices, these 2 by 2 matrices A, B, 3B, A, where A, B belongs to rational number Q. Q is the set of all rational numbers under matrix addition and multiplication is, correct option is 2, is a field. Let S is the set of all those 2 by 2 matrices A, B, 3B, A, such that A, B belongs to rational number Q, and since S is an integral domain, then S is a non-trivial commutative ring with unity and contains no divisor of 0. Let A is the matrix A, B, 3B, A. This 2 by 2 matrix belongs to S, and A, B belongs to Q, such that this order pair A, B not equal to this 0, 0. Then determinant A equal to A square minus 3B square. There does not exist any non-zero rational numbers A, B such that A square minus 3B square equal to 0. So we cannot find any non-zero rational numbers. Hence, obviously, A inverse exists, and A inverse equal to this 1 by determinant A and this A minus B minus 3B, this transpose of this determinant matrix A. This A inverse belongs to S. Therefore, each non-zero element of S, here capital A is the matrix, is a unit. Unit means multiplicative inverse exists for that non-zero element in S. Hence, S plus dot, here plus and dot matrix addition and multiplication over Q is a field. So correct option is this. Number 2, this integral domain, this is a field. Note that if the above example, this AB belongs to set of real numbers R, if this element A and B belongs to the set of real number R in place of rational Q, then there exist two non-zero real numbers A, say root 3 and B equal to 1, for which determinant A equal to A square minus 3B square equal to 0. Then A inverse does not exist, then S has no inverse, multiplicative inverse, and hence S plus dot is not a field. Next question. So correct option is 2. Next question, question 1b. Let A and B be ideals of a ring R. Choose from the following properties which holds for R. This option 1, 2, 3, 4, and which is the correct option. Next question. And note that this ring there are 9 properties, R plus commutative ring. There are 5 properties, R dot semigroup, 2 properties and 2 distributive laws, and so on. And from a ring we get commutative ring, additional 1 property is this R dot is commutative semigroup. There are 3 properties, so 10 properties, and ring with unity also 10 properties. Also there are 10 properties. This R dot is a monoid, that is multiplicative identity exists, and this commutative ring with unity, and this commutative ring, commutative monoid, commutative ring is a integral domain, and this skew field dot division ring. For skew field division ring there are 11 properties, R plus commutative group, R dot group, 4 properties of group, and 2 distributive laws, and commutative ring with unity, and this so this commutative ring with unity is the ring unity, and then addition commutative, multiplication is commutative. And integral domain, and for integral domain there are 12 properties, This R plus commutative group, R dot commutative monoid. The four properties: two distributive laws holds and contains no divisor of 0. That is, multiplicative inverse may not exist for integral domain. So from field is an integral domain, but every integral domain is not a field. Only finite integral domain is a field. And the field also, there are 12 properties: R plus commutative group, R dot commutative group, 5 properties, and 2 distributive laws, and field contains no divisor of 0 also. Next question, A and B ideals of ring R. Choose from the following properties which are hold. Correct option is A plus A equal to A. Now let R be a ring. This third bracket means, and double third bracket means, you can avoid this property from up to this in the answer booklet. Let R be a ring. Let A and B be two ideals of R. Then A plus B is the set of all those A plus B such that small a belongs to capital A and small b belongs to capital B, and this capital A into capital B, this AB is the set of all those this type of elements, this summation I equal to 1 to n AI bi such that AI belongs to capital A and bi belongs to capital B, and n belongs to the sacred natural number n. Then theorem states that A plus B and AB are ideals of R, and AB is a subset of A intersection B, and A union B is a subset of A plus B. A plus B is the smallest ideal containing both A and B, that is, A plus B is a subset of P, P be any ideal containing the both A and B. Number 4, A intersection B is an ideal of R. Number 5, A union B is an ideal of R if and only if either A is a subset of B or B is a subset of A. Number 6, if R be a commutative ring with unity such that A plus B equal to R, then AB equal to A intersection B. Now if we take first state this theorem from this theorem 2, from the statement 2, AB is subset of A intersection B, A union B is a subset of A plus B. If we take B equal to A, then obviously A union A is a subset of A plus A. A union A, put A in place of B, A union A is a subset of A plus A. And that is A union A means A is a subset of A plus A. Also, A plus A is the smallest ideal containing A. Smallest ideal containing A, because A plus B is the smallest ideal containing the both A and B. And so A plus is the smallest ideal containing A, that is, A plus A is a subset of A. Thus A is a subset of A plus A, and A plus A is a subset of A. Hence A plus A equal to A. Hence the correct option is 1, A plus A equal to A. Next question. So correct option is 1. Next question, C. Which of the following statement is true? Number 1, Z plus dot has no unit element. Number 2, in the ring Z6 plus dot, every non-zero element is unit. Number 3, the set of all unit in a ring R with unity does not form a group with respect to multiplication. Number 4, if A be unit in a ring R with unity, then A is not a divisor of 0. Correct option is 4, because we have theorem this: if A be a unit in a ring R with unity, this multiplicative identity unity means, then A is not a divisor of 0. You can see the book schema of page 218, theorem 3.1.8. So A be a unit non-zero element, this multiple inverse with multiple inverse in a ring R with unity. In a ring Z plus dot, Z is the set of all integers, addition of integers plus and multiplication of integers dot. 1 and minus 1 are the only units, as 1 dot 1 equal to 1 this, and minus 1 dot minus 1 equal to 1. Here this 1 is the unity, multiplied identity. So this 1 dot 1 equal to 1 and minus 1 dot minus 1 equal to 1. So z plus dot are only 2 units. So correct. So option 1, z plus dot has no unit element. Wrong. So option 1 is wrong. In the ring z6 plus dot, set of residual classes, z6 class 0 to class 5. Now class 1 and class 5 are units, because here the unity is class 1. So class 1 dot class 1 equal to class 1, and class 5 dot class 5, that is class 25, and this division by 6, 4, 24, so residue 1. So class 5 dot class 5, actually this dot is the multiplication modulo 6, this class 1. So class 1 and class 5 are units in this ring z6 plus dot. Plus is the addition modulo 6 and dot is the multiplication modulo 6. So the ring z6 plus every non-zero element is unique? No, only there are 2 units, class 1 and class 5. So option 2 is also false. Next 3, the set of all unit in a ring R with unity does not form a group with respect to multiplication. Now we have a theorem, the set of all units in a ring R with unity forms a group with respect to multiplication. Consult MAPA page 219, theorem 3.1.9. So option 3 is also false. Next, so correct option is only 4. A, B unit in a ring R with unity, A is not a divisor of 0. Option proof of this, since A is a unit in R, ring R, A inverse exists in R, and A inverse equal to A inverse A equal to I. I is the multiplicative identity, that is unity in R, and B be an element in R such that AB equal to 0. Then A inverse AB bracket AB equal to A inverse 0, that is my associative property multiplication. This A inverse A, this B equal to 0. So A inverse equal to I, B equal to 0. This implies B equal to 0. This shows that A is not a left divisor of 0. A is not a left divisor of 0 because AB equal to 0 here implies that B equal to 0. So obviously A is not a left divisor of 0. Let C be an element of R such that CA equal to 0. Then CA, A inverse equal to 0 into A inverse. This implies C into A inverse equal to 0. So this bracket replacing this C A inverse equal to 0. So C into I equal to 0. C this C I equal to 0. So I not equal to 0. So obviously C equal to 0. So C A equal to 0. So C equal to 0 implies C equal to 0. Hence A is not a right divisor of 0. So A is not a divisor of 0. So correct option is 4. A be unit in a ring R with unity, then A is not a divisor of 0. Next question. Correct option is 4. Next question, the ideal twice z plus dot in the ring z plus dot with the z denoting the set of all integers. Correct option is what? Option 1 a prime ideal, not a prime ideal. Option 3 a maximal ideal but not a prime ideal. Option 4 none of the above. Actually this we know, the ideal twice z plus dot is a maximum ideal as well as a prime ideal in the ring z plus dot. Actually this is the statement. So twice z plus dot is a prime ideal is the correct option, and as well as maximal ideal. And what is the prime ideal? In a ring R plus dot, an ideal P not equal to R is said to be prime ideal if A comma B belongs in R. AB belongs to P implies either A belongs to P or B belongs to P. Then this ideal P is said to be prime ideal of this R. The prime ideals in the ring Z plus dot are the ideals Pz plus dot, where P is either 0 or a prime. So here twice Z to each prime, so obviously 2Z plus dot is a prime ideal by this theorem. So the ideal twice Z in the ring Z, actually Z plus dot, is a prime ideal. Obviously prime ideal, so correct option is this, is a prime ideal, option 1. Next, let AB belongs to twice Z for some A comma B belongs to Z. AB belongs to twice Z implies AB equal to 2k for some integer k. So 2 is a divisor of AB, and hence either 2 is a divisor of A or 2 is a divisor of B. That is, either A belongs to twice Z or B belongs to twice Z, and hence the result twice Z is a prime ideal by the definition of prime ideal. Next, what is the maximal ideal? In a ring R plus dot, an ideal M not equal to R is said to be a maximal ideal in R if for any ideal S of R satisfying M is a subset of S is a subset of R, either S equal to M or S equal to R. Then this M is called maximal ideal. Theorem: the ideal Pz in the ring Z is maximal ideal if and only if P is a prime. So obviously twice Z plus dot, this ideal twice Z plus dot in the ring Z plus dot is a maxima ideal because P is prime here. Let S be an ideal of the ring Z such that twice Z is a subset of S is a subset of Z. Since Z is a principal ideal ring, S is a principal ideal of Z as well as all ideals in the ring Z are principal ideal. Principal ideal: the smallest ideal of a ring R containing an element A belongs to R is said to be a principal ideal of R. This ideal is generated by A and is denoted by this notation, this angle bracket A. Example: all ideals in the ring Z are given by Mz, where M is an integer greater than or equal to 0. All ideals Mz of the ring Z are principal ideals. Principal ideal ring, and so on. The ideal is said to be principal ideal ring, and then this, so on. Not associated with this question. So I write this, the prime ideal, and this right here this, and this proof up to this twice Z is the state this theorem prime ideal, this Pz P either prime, so twice Z is prime ideal. And also write that maximal ideal and Pz state this theorem ideal, this prime ideal, P is prime, this Pz is maximal ideal, so twice Z is the ring is maximal ideal. This is the sufficient answer for the marks 1 plus 1. 1 is for the correct option and 1 is the explanation. Next question. So correct option is prime ideal as well as maximal ideal. Option E, question E. In a field of characteristic 3, note that characteristic 3, A plus B whole to the power 6 equal to what? As 6 is not prime, A plus B whole to the power 6 not equal to A to the power 6 plus B to the power 6, and 6 cannot be expressed as P to the power n for n belongs to set of all integers Z plus. Frobenius identity: let P be a prime and F be a field of characteristic P, then A plus B whole to the power P equal to A to the power P plus B to the power P for all A comma B belongs to F. So only state this Frobenius identity and write this, and up to write this, and this is the correct explanation of this. No proof is given there, and this note that A plus B whole to the power 6, this binomial theorem, A to the power 6 plus 6 A to the power 5B plus 15 A to the power 4B square plus 20 A cube B cube plus 15 A square B to the power 4 plus 6 AB to the power 5 plus B to the power 6. Now 6 A to the power 5 into B, this is equal to 2 into 3 into A to the power 5 into B. this 3 into e to the power 5, this is equal to 0, because these characteristics, if characteristics f equal to p, then pa equal to 0 for all a belongs to f. We know this. So if characteristic of a field f is p, then p into a equal to 0 for all a belongs to f. So 3 into something, this is equal to 0, because f is a field characteristics 3. So 3 into this term 0, and 15, so 5 into 3 into this, so obviously 3 into this is also 0, but 20 cannot be divisible by 3, so this term not equal to 0, and this also 0, because 3 into something 6, 2 into 3 into something 0. So a plus b whole to the power 6 equal to a to the power 6, 20a cube b cube plus b to the power 6. We get this. So correct option is this none of these. Next question. If the number of idempotent element in J domain not independent. Idempotent element in J domain where m greater than 1, n greater than 1 are relatively prime is option 1 at least 2, option 2 at least 4, option 3 0, option 4 none of the above. So these are the characteristic ring with p characteristic p, then we can write this p for p3 we get this, and p9 we get this, p27 equal to this, and so on. And this question may be wrong, not independent, idempotent. And what is the idempotent element? An element x in a ring R plus dot is called idempotent element if x square equal to x. 0 element, additive identity, is an idempotent element in a ring R. In a ring R with unity I, 0 and I, the additive identity and I is the multiple identity, are idempotent elements. In a ring R with unity I containing no divisor of 0, 0 and I are the only idempotent elements. Now, here m is greater than 1, n is greater than 1, and the relatively prime, mn relatively prime, then zmn is isomorphic to zm cross zn. Here z6 isomorphic to z2 cross z3. Now z6 contains this class 0, class 1, class 2, class 3, class 4, class 5, and z2 contains class 0, class 1, z3 contains class 0, class 1, class 2. So this set class 0, class 1 cross sets this set class 0, class 1, class 2, we get this Cartesian product set is order pair class 0, class 0, class 0, class 1, class 0, class 2, class 0, class 2, and class 1, class 0, class 1, class 0, class 1, class 1, class 1, class 1 order pair, and class 1, class 2 is this. Now this isomorphic to this. Their idempotents Z2 cross Z3 are class 0, class 0 order pair, class 0, class 1, class 1, class 0, class 1, class 1. The preimage of class 0, class 0, this order pair, and class 1 and class 1 are class 0 and class 1 in Z6. So for this element, we get 1 on correspondence this 0 class, and this for this 1 class 1 order pair element, we get this class 1 element. Now we want to find the preimage of class 0 class 1, then let A equal to m plus 6z be the preimage of class 0 class 1, where 0 less than equal to m less than 6. Then image of A is this order pair m plus twice z for this m, and for 6z this m plus 3z. This equal to class 0 class 1. Now this equal to, we can write this 0 because this A is 0, class 0, class 1. So M is 0, class 0, and this class 1. So 0 plus twice z plus 1 plus 3z. So for this first component, so M, obviously this M is divisible by 2 because this is 2z, and for this 1 plus 3z, this M is modulo residue class this 1, and so this 1 modulo 3 congruent to 1. This M is congruent to 1 modulo 3. M is divisible by 2 and M is congruent to 1 modulo 3. 1 modulo 3. Now 4 is divisible by 2 and 4 is congruent to 1 modulo 3. So this A equal to 4 plus 6z. So class A is the class 4 is the pre-image of this class 0 class 1 order pair in Z2 cross Z3. So class 0 class 1, a pre-image of class 0 class 1 is class 4. And to find the pre-image of class 1 class 0 in Z6. Now M plus twice Z, M plus 3Z. This so this is equal to class 1 and class 0, and this is equal to 1 plus twice Z, and for this 0, so M is 0, 0 plus 3Z, this 3Z. So this M is divisible by 3 because this is 3Z, and M is congruent to 1 modulo 2 because this 1 plus twice Z we get. So A is the equal to M plus 6Z, that is M equal to 3. If M equal to 3, then M is divisible by 3, and 3 congruent to 1 modulo 2, 3 minus 1 divisible by 2. So class A is class 3. So the pre-image of this, pre-image of class 1 class 0 is class 3 in Z6. So class 0 image is this order pair class 0 class 0, class 1 is order pair class 1 class 1, class 2 this class 0 class 2, class 3 is class 0 class 1 class 0, class 4 class 0 class 1, and class 5 is class 1 class 2. Now class 0 square, that is equal to class 0 into class 0, this is class 0, class 1 square, this is equal to class 1, class 4 square, this is equal to class 4, class 3 square, this is equal to class 3. So class 0, class 1, class 3, class 4 are the only 4 idempotent in Z6. Note that if M greater than 1, N greater than 1 and relatively prime to each other, then there are at least 4 idempotent elements in Zmn. If n equal to p1 to the power m1, p2 to the power m2, pk to the power mk is the prime factorization of n as a product of powers of distinct primes p1, p2, pk, these p1, p2, pk are prime numbers, then the ring Zn is isomorphic to Z p1 to the power m1 cross Z p2 m2 power m2 cross dot 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 Z pk to the power mk. The number of all idempotence elements of Zn is 2 to the power k, where k is the number of distinct prime divisors of n. So this is the important theorem. So you write here only the at least 4 idempotent element, and this idempotent element, these are these at least 4 idempotent elements: class 0, class 1, class 4, and class 3. Next question G. For the subspace capital U is the set of all those matrices 0, 0, CD, and set V, capital V is a set of all those matrices this A, B, C, C minus C, these 2 by 2 matrices. Then dimension U and dimension V are what? Now basis of U, obviously this C and D are non-zero element, and this maybe non-zero element, this. So basis of U is this 0, 0. For C we can write 1, and for D we can write 1. So 0, 0, 1, 0, and 0 0 0 1. This two matrices, this set of two matrices is the basis of U. So dimension of U is 2. And basis of V, here three distinct elements A, B and C. So for A we write 1 0 0 1 0 0 0. For B put here 1 0 1 0 0. For C put here 1, so 0 0 1 minus 1, this. So dimension of V is 3. So correct option in dimension of U and dimension V is 2, 3. Correct option is 2. Correct option is 2. Next question H. Which one is not a vector space? C is the complex number over the complex number C. Option 2, complex number C over real complex field over real field, and this R real field over complex field, real field over rational number, field of rational numbers. Now option 3 is the correct option. This R over C is not a vector space because R is the set of real numbers, C is the set of all complex numbers. This mapping dot in circle such that C cross R maps R, and external composition of C with R, this scalar multiplication, is not defined because for every non-zero real number alpha belongs to R, and every complex number A plus IB, A comma B belongs to R, we would have A plus IB dot in circle, this operation alpha is equal to A plus IB into alpha. So A into alpha plus I into B alpha, not necessarily belongs to the set of real numbers R. So this mapping is not defined. So there are no such vector space structure here because this external composition is not defined here. So this is the R over C is not a vector space. Correct option is 3. Correct option is 3. Next question. Question I. Which of the following is a subspace of R3? Option 1, 2a plus 3b plus 5 is equal to 0. Option 2, 2a plus 3b plus 5 is equal to 1. Option 3, 2a plus 3b plus 5c minus 1 equal to minus 1. None of the above, where A, B, C, this order triplet belongs to R3. Let S be the set of all order triplet A, B, C belongs to R3 such that twice A plus 3b plus 5 is equal to 0. Clearly, this order triplet 0, 0, 0 belongs to S. So S is a non-empty subset of R3. Now let Xi equal to A, B, C order triplet belongs to S, A, B, C belongs to R, and twice A plus thrice B plus 5C equal to 0, and this equal to C equal to minus twice A minus 3B by 5. So Xi equal to A, B, C. Value of C is this. So equal to A common 1, 0, minus 2 by 5 plus B common 0, 1, minus 3 by 5. A into alpha plus B into beta say, where alpha is this and beta is this vector. This belongs to the linear span of alpha beta. So this Xi belongs to S. So S is a subset of linear span of alpha beta. Again, alpha belongs to S, beta belongs to S because this 2 into A plus 3 into B plus 5 into C equal to 0. For alpha is this, A, B, C is this, and for beta, A, B, C is this, 2A plus 3B plus 5C equal to 0. So obviously alpha belongs to S and beta belongs to S. And this implies linear span of alpha beta belongs to a subset of S. Hence, S is equal to the linear span of alpha beta. So S and alpha beta are linearly independent vectors in S. So alpha beta set alpha beta is a basis of this S, and dimension of S is 2. Dimension of these 2, alpha and beta. Now we have this subspace of this. So this, let gamma equal to a1 b1 c1, delta equal to a2 b2 c2 belongs to S. So since gamma and delta belongs to S, so by the property of S, twice a1 plus 3b1 plus 5c1 equal to 0, twice a2 plus 3b2 plus 5c2 equal to 0. Now alpha gamma plus delta, this equal to this. Now we check this whether this 2a plus 3b plus 5c equal to 0 or not for this gamma plus delta, and using these results we get 2 this plus 3 into this plus 5 into this equal to 0. Hence alpha gamma plus delta belongs to S. For all gamma delta belongs to S. Let gamma equal to this and k scalar belongs to real number. Then k gamma equal to this for all gamma belongs to S and for all k belongs to R. And this also belongs to S because this 2 into this plus 3 into this plus 5 into this also equal to 0. Hence S is a subspace of R3 over the field R. So first write this 0 0 0 belongs to S. This is non-empty subset of R3, and next prove this. This is the subspace theorem. Gamma plus delta belongs to S and k gamma belongs to this S. Then this S is a subspace of R3. So first option is correct. Option 1 is correct. Next question J. For a real symmetric matrix, eigenvalues are option 1 all real, option 2 all complex, option 3 cannot be ascertained, option 4 both real and complex. Theorem: the eigenvalues of a real symmetric matrix are all real. So real symmetric eigenvalues are all real, so option 1 is correct by this theorem. Now proof of this theorem: let A be a n by n real symmetric matrix, let lambda be an eigenvalue of A, then determinant of A minus lambda in equal to 0. In is the identity matrix of order n. This implies bracket A minus lambda in into x1 equal to null matrix O with some non-zero solutions x1, capital X1. So this implies A capital X1 equal to lambda into capital X1. This implies taking complex conjugate bar whole transpose on both sides. So we get this A x1 whole bar whole transpose lambda x1 bar whole transpose. This is equal to this x1 bar whole transpose A bar whole transpose and lambda bar x1 bar whole transpose, because lambda is scalar. So lambda bar whole transpose equal to lambda bar. So transpose is not affect this lambda because lambda is a scalar quantity. Then x1 bar whole transpose A because A bar A transpose equal to A transpose equal to A because A is a real symmetric matrix. This, so this A composing x1 from the right hand side. So this x1 and x1 from the right post multiplying on both sides by x1 capital X1. So we get this A x1 equal to lambda x1. So we get this and take this bracket lambda minus lambda bar is equal to null matrix. This lambda minus lambda bar equal to 0. So this because this x1 bar transpose x1 not equal to null matrix because x1 is the non-zero, hence lambda equal to lambda bar, hence And lambda bar is the complex conjugate of lambda. Hence, lambda is purely real. So correct option is all real. This completes the MCQ paper CC-6 2021. Thank you for watching this video.